Thank you. Good catch. Let me illuminate some things here, and in fact, erase the boards also. So I'm going to talk a little bit about geometric optics, and also say something about, tell you once again about the photoelectric effect, because it is such an important result in physics. Now we finally have the jet car, which I guess I'll do sort of in the middle of the lecture to wake everybody up. This, though, is a demo that I wanted to show you when we were discussing the conservation of momentum. Remember, the things that are conserved, for sure, are momentum, energy, angular momentum, and charge. There may exist other conservation laws, but we haven't yet discovered them. I guess I can illustrate some of this business with mirrors just from this web page, which I put a link to this web page on the class web page. And this web page starts out showing you a big convex mirror and smaller ones. And in a convex mirror, what you've got is that the light will come in and then, of course, bounce off. In the concave mirror, it's like this. And what you have is a light ray coming in either case will hit the mirror and bounce off with an equal angle. So, in other words, there is if you imagine the surface of the mirror, which is, say, curved, at any given place, it's, if you look at a small enough region, it's flat. And that, of course, is the basic idea of calculus, to look at things that are curved on a small enough scale, and then they become flat and everything's simple. In any event, a photon coming in that makes some angle with the normal, since this is locally flat, you can draw a perpendicular, and then if you have an angle of incidence here, the angle of reflection is the same as the angle of incidence. I may not have drawn it exactly right. And this is also true of this is a concave mirror. So you can think of this part that's enclosed here as a cave. And then there's a convex mirror here, where again, if you look carefully, if you look at a small enough region, then it's locally flat. You can draw a perpendicular, and the reflected light will have an equal an angle of reflection that will be equal to the angle of incidence. Here, why don't I try to move this out of the way, because we've gotten, I may have blocked what I was trying to show you. Here we've got two mirrors. One is convex, one is concave, and said, that basically it's that light from here hits the mirror and then goes out, and as I said, equal the angle of incidence is equal to the angle of reflection. The angle of reflection is equal to the angle of incidence. If we look at this thing and we bring it in close, you see that the image, which we call the virtual image, in the mirror of the reindeer is vertical. And by the way, what a mirror does, people always think that a mirror interchanges left and right. What it really does is it interchanges forward and backward. And so you look here and you see the nose is pointing at you, whereas here it's pointing away. Now as I move this back, there's a change, and then it goes upside down. To me, it looks upside down now, but I have to sort of move it there to see it upside down, because light is coming from here, bouncing on the mirror, and then coming back to me. If anybody wants to come down here and play with this, you're welcome to. The same thing is true of this big mirror. As I look at the big mirror, I'm upside down in the big mirror. And I think as you look at it, you're all upside down. I can move this a little bit closer. And so, I think you're all
pretty upside down.
Mm-hmm. Yeah, everybody's upside down because we're far enough away. On the other hand, when I go close enough, I then start to see myself right side up and huge. So this is the concave mirror. And mirrors, of course, are used everywhere. Most of the mirrors that we use are, we would like the mirror to be as flat as possible. So we get a nice reflection, and we can use it to shave or brush our teeth or whatever, floss maybe. But in astronomy, mirrors are used a lot to make telescopes. So what you have is you have a large mirror that collects the light and then focuses it on some detector, which creates the image electronically these days, although you can also arrange things so that you can look through, you can see the image with your eye. But today the most important measurements, apart from things that sort of just happened once and quickly, like a meteor or a, I don't know, something that just happens once or happens briefly, the scientific measurements with telescopes involve trying to measure something that hasn't been measured well before, trying to measure something better, and so you use a bigger mirror or a longer exposure. And in this case, you don't want to sit there with your eye for hour after hour. Instead, what you do is you have an electronic detector that detects and stores electronically all the photons that come in. Well, it doesn't store the photon, it stores the fact that the photon came in. And then recreates the image for you out of all that data collected over a long period of time. Okay, I think I'm going to move this out of the way also, because I don't want this jet cart to run into anything. What we've got here is this is a nice demo both of internal reflection and, in a sense, of lenses, although I don't know how easily I'm going to show the lens aspect. What we do is turn this light on, and I guess it's a switch down here. And so now we see for example, that when light, that's cute. You see at this angle, at angles less than about, what is it, about 30, 40, below about 45 degrees, we get total internal reflection. So the light comes up here and it hits the surface. Instead of zooming out into space, it just bounces back into the medium. That total internal reflection is what's used by waveguides for in fiber optics, which is how so much of our information today is transmitted. On the other hand, if you're greater than 45 degrees, and 45 degrees is just for this particular plastic and air. If you had water, it would be a different angle. If you had glass, it would be a different angle. But it'd be roughly in the range between 30 and 50 degrees, or between 20 and 50. And now what you see is it comes out like this. So you imagine that there's light from somebody's standing, suppose this were water and somebody was standing in a swimming pool. The feet would be down here, the light from the feet comes up, and then it goes out at this angle. The person standing here would see the light coming from here in this way and would assume that the feet are over here, and would think that the people in the pool have very short legs. Then, of course, when you get to water, a light going straight up, not much happens. And then, when you get to more than there, you get total internal reflection. I wish I could do a little more with this demo. All right, yeah. Okay, we can see something maybe about how lenses work. Let's see, it'd be light. Suppose this is a huge convex lens, if you think of it that way. Light coming in like that gets focused this way. Oh, that's interesting. All right, so let me do this. You see, as I move it out, the light is coming in vertically, but you notice it's getting focused. So that's how the lens works. How a convex lens works. And if I keep that point there, you see the light, all the light goes. Well, I've got to keep the thing. Well, this is let's see. There's a certain point here called the focus, and all the light should go through it, even as if I keep I want the light coming in to be always vertical. That's like light coming from infinity. And there's a point, as I do that, there should be a point up here that, well, at least in the thin lens approximation, there's a point up here through which the light always goes, and that's the focus. And I don't know if we saw it here, but you see as we go over here, the light goes that way, and then over here goes this way, and so it's plausible there's a point here where it almost goes through. Oh, that is to say that it almost, the light goes through that point almost always. Okay, any questions? Now, this is the photoelectric effect demo, and this time I've asked for a heat lamp. This is just an ordinary light, but it's not very bright because it's just a battery device, whereas this is 110 volts. And so what I want to show is, remember the basic equation that's now over 100 years old, due to Einstein, who said E equals H. I normally think of this as nu, but if I just write F for frequency, so to cut down on the use of Greek letters, then the energy of a photon is Planck's constant and the frequency, which is measured in basically cycles per second. So the units of frequency are 1 over seconds, or inverse seconds. Planck's constant, the units are energy times time. So there's joule seconds, or EV seconds, electron volt seconds, whatever. And let me see if I can quickly get Planck's constant. In EV seconds. Good. So in EV seconds, Planck's constant is 4.1, I'm going to round it off, 4.1 times 10 to the minus 15. Sorry, EV seconds. Is that too low for people to see? Maybe I'll write it here. H is 4.13 if you want, 10 to the minus 15 electron volt seconds. So that's the constant that basically tells you when a process having a certain energy and lasting for a certain time, when that process becomes classical and when it becomes subject to quantum effects. And basically, the process, the length of time, the duration of the process, the energy of the process times the duration of the process is less than Planck's constant, then quantum mechanics becomes very important. If, on the other hand, the energy of the process times the length of the duration of the process much greater than Planck's constant by, say, a factor of 100, 1,000, a million, a billion, then quantum mechanics is not important typically. Okay, so what we've got here as a process is I'm going to charge up this rod and if I do, the charge on the rod, let me do it some more. The charge on the rod makes this piece of metal pivot to a larger angle. Okay, now the question is, can we get the can we get infrared photons to knock the electrons off the plate? And so I'm shining them on it, and you see, even though it's pretty close, the infrared photons aren't able to knock the electrons off the plate because it's still at an angle of, I don't know, something like 45 degrees. Okay, so I'm going to turn this off now. And now I'm going to turn on this ultraviolet quartz lamp. This will be UV photons, which will have a higher frequency by a factor of, I don't know, 4 or something, maybe 10. And I'm trying to figure out where to position myself. So what I'm going to do first is I'm going to put a glass filter here, and the glass filter will block the UV. It takes a while for this damn thing to warm up. I used to have something that would hold the glass there, so I don't have to wait. Ah, here we go. Okay, now it's on, but the glass is blocking the UV. Which is why ordinary glass, well, if your glasses are made of glass, they probably block the UV. If they're plastic, then it's another thing. Now I'm going to pull the glass away, and you see quite quickly the electrons are knocked off the plate by the UV. So that was a physical effect that was noticed sometimes late in the 19th century, and then and it was puzzling to people because they could turn on various lamps, and they would see that nothing would happen. And then when they had UV, they would see the electrons knocked off. And the deal is that we're learning actually a couple of things here. The reason why the infrared light falling on the metal zinc plate, this is a zinc plate, but another metal would do, somehow zinc is better for demos. When the infrared light is shining, because it's a heat lamp, there's a lot of energy coming onto the plate. But the energy consists of gazillion low-energy photons that are hitting all over the plate. And you'd have to have 4 or maybe 10 of them hit the same electron to knock it off the plate. Whereas with the UV photons, each photon has quite a bit of energy, and so one photon hits one electron and knocks it off the plate. This tells us two things. One is that photons are small particles. They're not waves, even though where they go is determined by their wave function. Also, it tells us that electrons are tiny objects, because if they were big things that sort of covered the whole plate, then the infrared lamp would have done just as well. But instead, electrons are tiny particles, photons are tiny particles. Only when one high-energy photon hits one electron can the electron be knocked off the plate. On the other hand, both the electrons and the photons behave quantum mechanically, and what that means in particular is that where they go is typically uncertain, and the probabilities of where they go are determined by their wave function. And it's the square of the absolute value of the wave function that gives you the relative probability that a photon or electron would be at a particular place. So in other words, it is something like, for an electron we often use psi, and it's that squared is the probability of being at x is that, apart from, well, that times a certain unit of volume. So let me call that dV. So if dV is a certain unit of volume, three-dimensional volume, that times the square of the wave function is the probability that the particle will be there at a given time. So to put in the time, it would look like this. Equation would look like that. And then there are equations that govern what this is. The first such equation was Schrodinger's equation. The developers of the initial quantum mechanics were many people. I mean, Einstein, Planck was the first in a sense, because Planck introduced this constant to explain why the distribution of energy in a black body. So in other words, if you have some hollowed out cube and you heat the surface of the cube to some temperature, then the photons inside, you put a hole in the cube and measure the photons coming out. The intensity of the photons of a given frequency coming out as a function of frequency, it goes up and then back down. And he explained that by saying that each photon had a photon of frequency f had energy, his constant times f, the frequency. Planck himself didn't really go so far as to say that. I think his actual view was that what he was doing might have been just a mathematical trick for getting the correct distribution. Einstein then said, no, it's the real thing. There's more to Planck than what Planck wrote. You can give this strong interpretation. And he then used it to explain the photoelectric effect, which was a big puzzle. And in fact, that's what he won the Nobel Prize for, the first Nobel Prize. I think he got a second one for general relativity. If not, he certainly earned it. Of course, he also, in that same year, 1905, put forward special relativity. So, any questions about the photoelectric effect and Planck's yeah?
How does that little bar drop whenever the electron?
Why does the bar do what it does?
Yeah. How?
You know, I don't know. I was thinking about that, and all right. Let me just guess. I mean, I don't actually know. But I think you put the electrons on here, they spread throughout this whole region, and I think they spread through the region, and they also go to the small bar. So now you've got this small bar that has electrons, and this whole bar structure here has electrons. The electrons repel each other, and so you get the electrons farther apart if you swing it to 90 degrees. And there's a slight bias in this side, this this half bar is a little heavier than the other half bar. So it wants, because of gravity, to be vertical. But my guess then is that the electrons spread throughout this whole conducting medium. All this metal is conducting, of course, it's all connected as far as I can tell. So the electrons go everywhere. And in fact, they go exactly where they minimize the electrostatic energy of the whole system. And then, because there are electrons, let me grab this. In other words, you've got electrons here and here, so this is negatively charged, and now you've got this bar, which is also negatively charged. And so, if it goes out to this position, then it keeps these electrons far away from those electrons, and that lowers the energy. So I think that's what's going on. Any other questions, though? You might ask why it is that, how this transition is made from quantum effects to classical effects. And the real reason is that this amplitude here, psi of x, I guess everybody can see this board. So psi of x and t is really a sum of e to the I S1 plus e to the I S2, apart from normalization, plus e to the I S3, where each of these s's, and I should say this is divided by, it's divided by Planck's constant and multiplied by 2 pi. So it's 2 pi I over Planck's constant. And you sum over all possible processes that take you from the source of the particles up to the point x at time t. And the s's are the actions of the process. In fact, they're the classical action of the process. But they're arbitrary processes. They're not processes that obey classical equations of motion, like F equals ma and so forth. And so they're just all possible ways of going from the source to some point x. And so one way is just straight, another way is to do that, another way is to do this, all different ways of doing it. Now, if the size of these processes is about the same as Planck's constant, or let's suppose that these processes are so short that the action is negligible, then the amplitude is really independent of x and t, because all these phases are just one, and so you just get one a bunch of times and normalize it, and you just get one, and that's true independent of whether x is here or down there or over there, if the processes are all so short in time and energy. So in other words, on short time scales, virtually anything can happen. And so that's the basic idea that in quantum mechanics, all kinds of things that appear strange to us because we normally think classically, our experience is mostly classical. This seems very strange to us that all sorts of different things could happen. This particle starting out at a given place could go to an arbitrary other place if all these points are close and the time interval is very short. And so the energy of the process to go from one to the other is very low. On the other hand, If we go into a region where the S is of the order of Planck's constant, then these things are no longer all one, they're particular phases. And then for some x's, you'll get a bigger, the sum will be bigger. For others, the phases will all cancel. And so that's not going to happen. Then you come to the classical limit, where all the s's are big compared to Planck's constant. And then the necessary, then these phases, all these s's are huge compared to Planck's constant. So this is e to the 2 pi I times a billion or a million. And that means that if you consider a path that goes like this, and then you have another one that is almost the same, just slightly different, it will add because it's almost the same path, so the action will be almost the same. And now I should say that if that's true, that is to say, if there's a way of getting from x0 to x such that the neighboring paths that differ very slightly from one path, there's a whole bunch of paths that have the same phase, almost the same phase, then you get a huge amplitude and the probability is great. The answer is that quantum mechanics will tell you that the probability of being here is large. On the other hand, there might be a point down here such that there are some processes that get there, but all the other processes that get there have substantially different action, even if they're very close to this process. That's something that does not happen, quantum mechanically. Or it happens with a very low probability because the amplitudes add, but cancel. And so you get a very small probability when you add them all up. And so then when you go into the classical regime, in fact, now we're in the classical regime where these are huge compared to h. In other words, the action is a billion, a trillion, a gazillion times Planck's constant. And in that case, the only processes that happen are the ones such that there are a whole bunch of neighboring processes that have almost the same action. And those are the processes that satisfy the classical equations of motion. So classical physics happens automatically when the energy times the duration of the process is big compared to Planck's constant. And Planck's constant, you see, is very small. 10 to the minus 15 times 4 times an electron volt second. So that's really small. Okay, any other questions?
So when we're still talking about, we're measuring the behavior of photons or how they interact with electrons. So,
Here, I'll get it.
Oh, thank you.
So what now?
So when we take this equation, we're measuring the probability of the outcome of or photons when they get sent.
Photons, electrons, anything.
Okay.
Everything obeys quantum mechanics as far as we know.
Okay. So just any particle. Any particle.
Yeah, the amplitude for any particle to do anything
Okay.
is a sum of these exponentials, and these are all phase factors. So if some of you haven't been in a math class recently, e to the I theta is cosine theta plus I times sine theta. So these phases are a real number plus I times another real number. So they're really points on a unit circle in the complex plane. And just to make this a little more real for those of you who haven't seen complex numbers before, if you have a complex number x plus iy and you add it to another one, u plus IV, well, of course, it's x plus u plus I times y plus v. And if you multiply two complex numbers, then what you get is xu minus yv, because I squared, I times I, is minus 1. And then you get I times yu plus xv. So that's how complex numbers work. Those are the phases, and that's how quantum mechanics works. So this is one part of quantum mechanics. The other part of quantum mechanics is this business of states. And the states part was the part that was mainly introduced by Heisenberg. Not the one who made drugs in Albuquerque, but the German physicist who was one of the inventors of quantum mechanics in about 1925. He is the one who introduced the uncertainty principle and showed that if you measure the position of something, say the position in this direction, then very, very accurately, then necessarily its momentum in the same direction becomes much less certain. And what that means in terms of these wave functions is, if you, well, it can be illustrated, I've done it on the laser demo many times. If you have a laser beam coming through a slit, and you make the slit narrower, the spread of the beam on the screen gets wider. And the reason it gets wider, well, each individual photon goes through the slit, goes to a particular place on the screen. But the wave function, when it's being compressed in space here, its Fourier transform effectively, it gets spread out. Anyway, the wave function is such that it tells the photons coming through, okay, you're going through that narrow slit, then you have to acquire a momentum in this direction with a certain probability that's pretty big. And so this beam spreads out. So the wave function tells the photons to spread out. Okay, now I've got a couple of, this is a gee whiz demo. And it's a little bit scary. I'm easily frightened, however, so it's, this is a Tesla coil, and what it is it's basically a transformer that takes 60 cycle, 110 volt current, and changes it to a much higher voltage, but less current in this coil. And the result is that the air is ionized and electromagnetic waves are radiated at so photons are radiated. All right, so you see, in fact, this thing is glowing. In fact, I can also see electrons jumping off the tip of that coil. And that's because the tip of the coil has incredibly high voltage. So high that the electrons just say, screw you, I'm out of here, and jump off. We've got other tubes here, and I'll try not to drop any of them. This is a different tube, has something else in it. I think it has neon or some other rare gas. In fact, what I should do, let me turn this off for a second, turn some of these lights down so that you can see this better. Yeah, I'll turn them all off. Let me get a quick shot of it. All right, I'm going to turn it back on now. So now you can see the electrons zooming off the Tesla coil. Notice the light is blue. It's blue because these electrons have energies much higher than 1 volt. Now as I move it closer to here, you can see the thing light up. And the same thing with this one. And I don't know what, oh, it's just paper. So I'll show you this one more time. What might be fun, now that I think about it, would be to combine this Tesla demo with one of the other demos that I showed you about a month ago, the one that had all those parallel tubes of different gases.
Oh, yeah.
And then we could zap them all with the Tesla coil and see what would happen.
That'd be cool.
I think I'm going to put both of these back there so they'll have less of a chance. So any questions? You see, the advantage of alternating current is that you can, with a transformer, you can up the voltage. Yeah.
What happens if you touch the tip of this Tesla coil?
I'm sorry, what happens if what?
Can you touch that? The tip of it?
If I touch the tip of it?
Yeah.
I don't know. We can find out if you touch the tip of it. But I don't recommend it. You probably get a shock and it might burn you.
Do it.
No, I don't.
Do it for a candy.
I mean, we have big rules of not injuring students, okay?
I want to see one live.
Professors they don't care about, but the administration doesn't want students to get hurt.
I'm down, dude.
I would say it would be, you might burn yourself, so let's just not do it.
We won't see the physics of carbon.
Okay, well, here's another demo, and this is a very different demo. Let's see. When the frequencies are very high, the wavelength's very short, then the wave properties are harder to see. On the other hand, when the frequencies are much lower and the waves are longer, then the wave properties are easier to see. And the visible light is sort of in between. You can send visible light through a diffraction grating and you get a pattern on the screen. And we've done that a couple of times. Here what we've got is much longer wavelength. Remember that visible light is about half a micron, half a millionth of a meter. Or 1/2000th of a millimeter, let's put it that way. And that's pretty small. That's too small for us to see easily. But this radiation, these are photons that are guided by 3-centimeter waves. And so the wave properties are much easier to see, and in fact it's hard to see the particle properties at all, because in order to detect these are photons of such low energy, because the waves are so long, the frequency is so low, that that each individual photon has almost no energy at all. Okay, so let me turn this on. And what do we have here? What we have here is a receiver and a transmitter. The transmitter is sending out 3-centimeter long radiation. So a wave that goes out It goes out and it bounces off this metal screen and comes back. It also bounces off this cardboard screen, and when it does, some of the light goes this way and comes back. And similarly, some of the light that goes here and bounces back bounces off this and comes in here. And so what you can get is you can get interference. And at the receiver here, you can arrange that the amplitudes, that the two waves coming in, one from here and one from there, cancel. And so I'm going to turn this thing on. Well, I'm not sure where I turn it on now. I can, okay, now that's the transmitter. I don't see the switch, damn it. Well, this is not going to work very well if I can't turn it on. It's the receiver that I'm not able to turn on. Maybe I should turn the lights on so we don't need darkness in order to do this demo. All right, does any student see the on switch? Volume. Oh, here we go. Okay, it was always on, it's just that, all right, it's not the loveliest of tones, but, okay, so we've got the radiation coming here and it's detected there. And now what I can do is I can change this distance and get some interference. Ah, you see? So, in fact, if I look down here, I see the biggest sound is about 85.4. go. In this case, they're very simple and they have a long, they're 3 centimeters long. So, I'm just trying to find it. Yeah, all right, let me do it here then. So in other words, let's put it this way. So the things are, the wave looks like this. The waves look like that. And if you have two waves that are coming in, let's say one of them is yellow, and they're in phase, then they add. So the total looks like that. And so then the question is, how do we get them in phase? Well, if the wave is, coming out of the transmitter, bouncing off a plate, going down here, and then bouncing back, and then going to the receiver. So if we change this by a certain amount, the total path length changes by twice that amount. And so if you move it by 1.5 centimeters, you've gone a whole wavelength, and these guys are in phase again when they hit the receiver. And that's really how all of the interference things work. It's that these waves that tell the photons where to go, the amplitudes add. Under some conditions, they cancel. Under other conditions, and they just come out to some medium value in other configurations. So, for example,
Oh, excuse one more question.
yeah, all right, hold on. Let me get more candy here.
So, are they sound waves or are the waves of measurement?
They're waves. Great question. Sorry. We call them light waves, but what they really are is quantum mechanical, mathematical structures that tell the photons where to go.
So how is it like coming out of the speaker and sound? What makes the speaker?
Oh, the speaker is, what we've got here is an electronic device.
Okay.
An electronic device that is sensitive to this, to these these photons, and it picks up an electrical signal and transmits it over here. And these photons are how shall I say?
Well, aren't they?
They're basically all in phase, so that each photon carries an electromagnetic field, and these fields are in phase. All right, it's a little hard to explain.
Well, they would leave the speaker as the speaker unit picks up an electrical signal, because it has the same. So the speaker has the cone inside that oscillates. And what we're hearing is the pressure waves, like just air that's coming out.
Oh yeah, when you hit, yeah, that's here. There's the speaker.
Mm-hmm.
So the electronic signal goes to the speaker, which generates the sound.
Right.
So you're hearing the sound wave, but it's picking up the photons.
Right.
And the photons are generated in a way such that they're all more or less coherent, and they're all in phase. And another way of saying that is that the wave that's guiding them is the same wave guiding all of them. The number of photons involved here, of course, is it's a crazily large number. It's like Avogadro's number. Okay. So does anybody else want to play with this?
I had my phone on that.
And,
So does moving the other two plates do the same thing?
yeah, if I move these, it should do the same thing. With the same distance also. Okay. Shall I turn it off? Or you want me to do something else with it?
That's fine.
Is there much else you can do with it?
What?
Is there much else you can do with it other than that?
Well, I don't know. Why don't we go to a node? Because, oh yeah, there is something else we can do. Hold on. Polarization.
Oh,
So, here we've got pieces of metal that are parallel to each other. And remember that in this wave there's an electromagnetic field through all these photons. And so what I can do is I can polarize this thing. Wow, that went just to 0. I don't know why it's going to 0. I would have thought that it would have cut it by a factor of 2. Let's try the other one. All right, for some reason, one of them really, oh, this thing may be polarized that's coming out. And that stands to reason because, after all, if you're making an electromagnetic wave by moving electrons back and forth, you're not going to move them back and forth and also up and down. So apparently the stuff coming out is polarized this way. And I'm actually having to think more about this. I haven't thought about this recently. But what I'm thinking of is that the polarization is up and down. And when we put in these vertical conductors, all the electrical energy gets absorbed by those wires. And the electrons move up and down the wires, but because of resistance and so forth, the signal's attenuated quite a bit. Whereas if the electric field is like that, and we put the wires in like this, then it starts moving the electrons a little bit in the wires, but the wires are very thin, so it can't have it much. See, we really cut things down. So that's apparently what's going got nothing there. If we put this plate down, then most of the wave is reflected. On the other hand, if we put that down, some of it's reflected. And of course my arms sometimes get in the way and have an effect. All right, I'm not sure. Oh, what else to do there? Let's. Yeah, this is interesting. Because you see, by putting this thing in, now we're getting a little bit of reflection from this thing. In other words, this thing that was blocking the signal is now reflecting it. And that sort of makes sense because, after all, this thing that was reflecting it, now it's going to completely block it. All right, I think we've got most of that straight. All right, anything else? Do I owe you another candy?
Yes, so.
All right, any other questions? All right, look, it's a really rainy day, and
What about, you didn't do that demo, did you?
Oh,
You didn't
I'm
do
sorry,
that demo
what?
over there, did you?
the jet
oh
car?
Christ, yes! I forgot all about it.
Oh, no, speakers are pretty durable.
It still sounds like it's still
Yeah.
going, so...
It made a real different sound there, yeah. Thud.
Okay, I turned it off. All right, well. Yeah, this is a demo that they had trouble getting. So I'm going to put ear protection on. And, okay, we've got compressed CO2 in the cylinders. It's going to blow air this way, and by conservation of momentum, I've got to go that way. This is a little scary because
That was loud.
last
I was
time
not
I did
expecting
this,
that.
the
My ears are ringing.
Yeah.
cylinders were old and had very little gas in them. Whereas here, God, I could get up to 20, 30 miles an hour, and I don't want to do that.
That's a good one.
Okay, all right, so class is over. I hope you had this in the...
Oh,
Yeah, you gotta do it
I
again.
had part of it in the camera.
All right, I'll do it.
Oh god, I can't spare my ears this time. My poor eardrums. Oops.
That was a good one.
Oh no. My ears.
Okay, that's enough. Nice to see you.
Thank you. Build me one of those class on Thursday. Steering wheel.
Yeah, where was that?
Yeah, I was gonna invite one of you. I was gonna suggest that one of you might wanna do it, but I'm afraid you'll get hurt.
I think I would
You're
overcompensate.
braver than I am.
Thank you.